Hi guys, welcome back to Bison Maths. I've been teaching maths for over 10 years now and really wanted to share some of the things that my students have found the most useful over the years. I'm making a series of videos on everything that you need to memorise for your A-levels, and this time I'm doing one for further maths on Core Pure Year 1. If you haven't seen the other Everything You Need to Memorise videos, then you can go to my homepage and check them out. You can also see that I've got hundreds of video tutorials that should help you on anything that you need a little bit of extra guidance on from the Pearson edXL textbooks, and they're filmed live with my real classes at school. Anyway, onto the video. Further Maths has got an awful lot of things to memorise and to understand, and actually there's not very much in the formula book. I've indicated on the memory page everything that's in the formula book with a little blue F. And there's actually so much to try and memorise for further maths that I really do recommend using the formula book to grab those ones if you need them. So, memorising in maths does three really important things. Number one, it's going to save you time. The second thing that it's going to do is make you feel really pro and really confident at the topic that you've got all of that knowledge about. The third thing is that it's going to help you to solve problems by spotting connections between different topics. And that again is an excellent thing to have. So, on to Core Pure Year 1 and everything you need to memorise. Okay, so here is the whole thing that we've got. I've organised it by chapter number here, and we're going to try and do this all in one take. So, we're going to start off with complex numbers. Now, the Cartesian form of complex numbers, nice and easy, is just that z equals x plus I, y. The modulus argument form is where you have r as the modulus, and then you're going to have cos theta plus I sine theta, where theta is the argument. Now, complex conjugates, the roots come in conjugate pairs, and we also need to know that z star, which is the complex conjugate of z, is going to be x minus iy. Now, to realise the denominator, that means really dividing complex numbers here. You just multiply by the complex conjugate. So you're going to multiply by 7 plus 2i and 7 plus 2i, so you don't just change the size of it. Now, for multiplying complex numbers, you need to know that you multiply the modulus and you add the arguments. For dividing complex numbers, you divide the modulus and you subtract the arguments. You also need to know about manipulating this particular modulus argument form, which is where instead of it having a plus in the middle, you actually have a subtraction. And the way that you can switch this is by changing the argument to minus theta, and then you can change it to plus I sine minus theta. And once you've got it with this plus form, it's then in the standard form that we usually work with. So we're now going to think about loci on Argand diagrams, and this one that we've got here is the perpendicular bisector of z1 and z2. So if I imagine having z1 here and z2 over here, there is the line segment connecting them. This loci that we have here is the perpendicular bisector of z1 and z2. The second one that we have is going to be a circle which has radius r, and it has centre z1, which is a complex number. And then this last one is going to be a half line drawn from z1, and it's going to be of angle theta. So that's all you really need for complex numbers in year 1. Then we're going to have a look at series that we've got here. So there's some standard results that we need to know about. So first of all, the sum of from r equals 1 to n of k is just going to be kn, and k here is just a constant. The sum from r equals 1 to n of r is just a half n plus 1. Now these next two are in the formula book, but actually I remember these. I actually remember the cube one first, because the cube one is the r1 all squared. So you square the half to get a quarter, the n to get n squared, and the n plus 1 to get n plus 1 squared. Now the sum of r squared, even though it's in the formula book, it's a sixth n plus 1, 2n plus 1. A couple of things I want you to notice here. For the sum of r, there is just an n and another n here. For the sum of r cubed, there's an n squared and an n squared, so there's 4 n's. And so for the r squared, there needs to be 1, 2, 3 n's overall. If you have the starting value that is not r equals 1, then you need to go from r equals 1 to n of f of r, and you subtract from r equals 1 to the one before, so it's going to be k minus 1 of f of r. Having a look at roots of polynomials now. So the sums of the roots and the pairs, etc. I'm going to just do it for a quartic, knowing that you can simplify it for quadratics and cubics as well. So the sum of the roots is just minus b over a, then it goes c over a, then minus D over A, and then E over A. So you can see down here I've got the sum of the roots, the pairs, the triples, and then all four roots. And you'll notice that they're all divided by A, and they alternate between negative and positive, starting with B, then C, then D, then E, in the order of the alphabet. So the sum of the squares now, this is saying the sum of the squares of the roots. Well, the way we work this one out is we do the sum of the roots, all squared, minus 2 times the sum of the alpha betas. And obviously with a quadratic, there's not going to be a sum of the alpha betas, it's just going to be alpha beta. Now the sum of the cubes is one of the hardest ones to remember because there's so much to it, but I think we can use the sum of the squares to help us to do this. So it starts off in the same way, but because it's cubes, it's not going to be squared, it's going to be cubed here. And also because we're talking about cubes instead of squares, we're going to switch it from a 2 to a 3. And rather than just having alpha beta, we also need to multiply it by the sum of alpha as well, so that here we've actually got 1, 2, 3 things. Then the last little bit is that we add on 3 alpha, beta, gamma. And we only need to know this one for cubics because it doesn't actually apply for quartics here as well. And then we're going to talk about the transformation of roots here. This is the linear transformations of roots of polynomials. If the roots are a alpha plus b, set w to equal ax plus b, then you rearrange for x to make x the subject, and then you substitute in. Okay, and that will give you an equation that is in terms of w. So the next thing that we're going to be looking at here is volumes of revolution. So volumes of revolution, if they're going about the x-axis, it is going to be from a to b, and it's going to be pi y squared dx. If you're going about the y-axis, again, it's going to be between a and b, but that's going to be on the y-axis this time, and it's going to be pi x squared dy. Just notice that if it's dx, this a and b is referring to the x-axis. If it's dy, then these a and b are referring to the y-axis. These things you probably know, so you may think it's a bit silly I'm including these, but you need to know the formula for the 3D solids. A cylinder is pi r squared h, and a cone is a third pi r squared h. Here we come to one of the bigger topics now, which is matrices and the properties of matrices. So first of all, we have non-commutativity. So this means that AB does not equal BA, the order matters. There are, of course, some matrices where it will be equal, but as a general rule, they shouldn't be equal. Associativity, this means that AB and then multiplying it by C is the same thing as doing A multiplied by BC, so that the order, if they're in the line, it doesn't matter if you do AB and then times it by C, or if you do BC and then times it by A. So the identity that we have here is that A is the same as having A and multiplying it by the identity matrix, which is also the same as having the identity matrix and multiplying it by A. Either way round, it's going to give you the A matrix. So now we're going to think about matrices, and in particular the properties of the inverses. So the definition that we have here is that A times A inverse is just going to be the same thing as the identity matrix. And that's the same thing as doing A inverse multiplied by A for that bit that we've got there. The product of inverses says that if you've got AB and you're doing the inverse of that, that is B inverse multiplied by A inverse. So the order actually reverses for when you're doing the inverse of a product of two matrices. Now the determinant, I've already drawn on this little cross. The determinant of a 2 by 2 matrix is just going to be the first diagonal, which is AD, and you're going to then subtract the second diagonal, which is BC. So nice and easy for a 2 by 2 matrix. For a 3 by 3 matrix is where things get a little bit more complicated. So you start off by having the A to begin with, and you're going to multiply that by crossing out these bits you've got here. You're going to multiply that by the determinant of the remaining elements, which is E, F, H, I. Now the next part that you do would be with B that you have along the top, except you need to notice it's going to be a subtract B. And again, you would cross through, and the remaining elements you have would be D, F, G, I. And then at the end, it would be a plus C, and the remaining elements you'll be finding the determinant is D, E, G, H. So the most important thing here is that you remember that it's a subtract for this bit. Now, if you wanted to, you don't have to use A, B, and C as the values. You could do A, D, and G, and then do the determinants of the remaining 2 by 2s. But it would go A minus D and G. It works for doing columns and rows in the same way. So if the determinant of M is equal to 0, then this means that M is singular. and if the determinant is not equal to 0, then it is non-singular. Singular matrices have got no inverse. Now we're going to talk about what the matrix of minors actually is. So to find a matrix of minors, you draw a cross through a particular element, you find the determinant of the remaining part, and then you replace the original element with that determinant. So for example, if I was going to find the minor of this D, you would cross through here, you would cross through here, you would find the determinant of the B, C, H, I. You would then replace this element here with the determinant of that BCHI part. So the matrix of minors is going to be when you apply that to the entire matrix. So each element is then replaced with its minor. So the matrix of cofactors is when you apply a pattern to the matrix of minors, and the pattern that you will apply starts with a plus, and it's then going to alternate between plus and minus. So it's going to go minus, plus, minus, plus, minus, plus. And the way I see this is there's this kind of cross shape of these plus ones, and the remaining parts are just going to be filled in with minuses. So the transpose of a matrix, this is where the rows and columns swap over. So I've just done a small example. If A is 1, 2, 3, 4, the transpose will be 1, 2, 3, 4. And you can see how that row has become a column and vice versa. So to do the inverse of a 2 by 2 matrix, you do 1 divided by the determinant of that matrix, and then you need to be careful here that you do some swapping. So instead of having A in the top, you're going to swap it with D down here. You then keep B and C in the same place, but you negate them in this way. For a 3 by 3 inverse, the inverse is going to be 1 over the determinant of A multiplied by CT. And I've said here where C is the matrix of cofactors, so you'll do the matrix of minors, then you'll apply the crisscross pattern of plus and minus, and that gives you the matrix of cofactors. But notice I've put this T here because there needs to be the transpose of that matrix as well. So a matrix is self-inverse if A is equal to its inverse, which kind of makes sense. The next part here, there's not going to be so much to fill in. It's more going to be thinking about systems of equations and a particular flow diagram that I've drawn here. So first thing you should do to try and think about what's the geometric situation that's represented by a system of equations is you should check the determinant of that matrix. If the determinant is not equal to 0, the only thing it can represent is planes meeting at one point, and that sort of black dot that I've got there is the point where those 3 planes are meeting. If the determinant is equal to 0, the next thing you should do is check the consistency. And I've got a video that I will link that tells you about how you check the consistency of equations. If they end up as consistent, it means that there are actually some solutions to those system of equations. And so it can either be a sheaf or it can all represent the same plane. And hopefully what you can see here is that there's obviously solutions. Here it is the solutions along this black line, and for the same plane, anywhere on this plane would be a solution because it would make all 3 of them true. So I just wanted to break down what I mean by being the same plane. These planes here are all identical to each other because they are just multiples of each other, including the right-hand side. So this one has all been doubled, and this third one has the first one all multiplied by -10. So they are actually the identical plane. Let's say you checked the consistency and actually they were inconsistent. This means that there are no solutions that exist. So what you should do next is you should check to see if any of the planes are parallel. If the planes have none of them as being parallel, the only option that it can be is a prism, and that is what it looks like here. You can see that there is no place where all 3 planes are crossing together. You could have an option where 2 of them are parallel, which is like this situation, or all 3 of them could be parallel, like this, and you just need to say that the geometric interpretation is that some of the planes are parallel. So I just wanted to show you here that these 2 planes, as an example, are parallel because I've got the same coefficients for x, y, and z, but I've got that they're equal to something different on the right-hand side. And you may require needing to manipulate them so that you can compare the coefficients directly. Notice how that makes them different to the same plane. The same plane would have had the same number on the right-hand side here. So that's my flow diagram for the systems of equations that we've got there. We're now going to have a think about linear transformations. This is something that's not majorly in the textbook, but I've seen it pop up quite a lot in exam questions. So first of all, for this matrix, if you're multiplying it by the point xy, if it's an invariant point, it will give you the exact same coordinate, xy. An invariant line, though, is a little bit different. It's not necessarily going to give you exactly the same coordinates, because that's just going to be an invariant point, but it is going to give you some multiple of that, so that the points may not end up in exactly the same place, but they will still end up in this proportion that we've got here, so that they're on the line. Now, I've got an invariant line that is not going through the origin this time. So this one is a y equals mx plus c. And I've already written this one out here because this is a very special case that I've only seen come up in one exam question. And I will link a video to how to do this because it's kind of tricky. But generally what we see here is it's still going to be in the same proportion, but that we replace x with just x dash, which is just another variable, a constant that we would have between them. So with linear transformations, the area scale factor, we know that the area scale factor is just going to be the determinant of the matrix. So the linear scale factor would be the square root of the determinant of that matrix. So for successive transformations, if we had PQ, this actually means that it's Q first and then it is P. So it is Q, then P here. Now this rotation theta anti-clockwise about the origin, this one is given in the formula book, so I'm not sure I would necessarily memorize this one, but it's going to be helpful for how we can use it for some of the others in just a second. So for the reflection in a plane, these ones are really simple. These are actually just the identity matrices, but for reflecting it in x equals 0, we're just going to negate the x column. For in y equals 0, we negate the y column, and for reflecting it in z equals 0, we negate the z column. So let's now return to the idea of this rotation. This time we're doing some 3D rotations and we're doing theta degrees anti-clockwise about the x-axis. So we're going to use this information that I've got at the top here. For the x-axis though, you keep the x row and column, the first row and the first column, the same. And you're then going to replace this other part with the rotation matrix, which is going to be cos theta minus sine theta, cos theta. So that's taken from the formula book. Now for the y-axis, you're going to keep the second row and the second column the same. And this is the twist, okay? So this one's going to get a little star next to it. You keep them the same. So there's going to be cos theta, sine theta, and sine theta. Normally, the negative is in the top right, but whoa, this time the negative is going to be in the bottom left down here. Okay, so you need to make sure that you put the negative in the right place for this. Now for the z-axis that we've got here, again, you keep the third row and the third column the same, and you're just going to replace with the rotation matrix, which is cos theta minus sine theta, cos theta. Not in the formula book, but I feel like it should be. If you wanted to undo a transformation like this one we've got here, well, you would need to undo Q by multiplying it on this end and P by its inverse on the beginning. So you just need to be careful about the order of trying to do those inverses. So let's go now away from matrices and we're going to have a look at proof by induction. So the steps for proof by induction, there are 4 steps. You first of all look at the base case, which is when n is equal to 1. The assumption is that n is equal to k, and that is true. And the inductive case is when n equals k plus 1. The 4th statement is going to be the conclusion, and the conclusion should be, since true for n equals 1 and true for n equals k plus 1 when assumed true for n equals k, it is true for all members of n of the natural numbers or n of the positive integers or whatever it's asking about in that question. So for divisibility, for the inductive, you should try and use f of k plus 1 minus f of k to help you find out that f of k plus 1 is divisible. And there's some tricks on that you can have a look in some videos that I'll be putting on as well. Now I've put some recurrence here because recurrence isn't actually in the textbook, but I've seen a question come up by the exam board in one of their mock papers that included a recurrence proof. So I wanted to mention this. If you do have a recurrence where the u of n plus 2 is in terms of un plus 1 and un, you need to check 2 things for the base case. You must check n equals 1 and n equals 2 for the base case, and you should also assume that it's true for n equals k plus, for k, sorry, and n equals k plus 1. So you need to do twice the number of assumptions because the formula is based on 2 different things that we've got here. Now we're moving on to the biggest part. If you have a look at the rest of what we've got here, it is all vectors. So we're going to go through some of our vectors definitions, and it's not surprising that vectors is one of the biggest parts because the vectors we do in regular maths is not very challenging. So this is where all of the vectors content has now moved to. So the scalar dot product, we've got A dot B. Well, we know that that's going to be the modulus of A times the modulus of B times the cosine of the angle between them. And when we're talking about the angle between two vectors, it's always the angle measured as they are moving away from each other like this. To find the dot product of two numbers as well, you just multiply the i's, the j's, and the k's and add them together. That's how you'd work out the left-hand side. So if A dot B is equal to 0, A dot B is equal to 0 if A and B are perpendicular, and that's a really important property. The vector line of an equation, R equals A plus lambda B, and here it's obvious that A is a position that is on the line, B is the direction vector of the line, and R is a general position that is on the line. The Cartesian line equation, well, this is in the formula book, but these A's here are all linking back to the position that's on a line, and these B's here are all linking to the direction of the line that we've got. Now we're moving on to the parametric plane equation. This one's in the formula book, but it's not actually that helpful. I think it's just common sense, this one. So R equals A plus lambda B, so the line equation, plus mu C. This time though, this is a position vector that is on the plane, this is a vector that is on the plane as well, and this is a vector that is on the plane. So it's a position vector and then two vectors which are parallel to the plane or actually included on the plane. Then we have the scalar product plane equation, and this is where r dot n, where n is a normal vector to the plane, is equal to a dot n, and a dot n is actually just going to be equal to some constant, so it's just equal to d or c, or whatever we want to call it. The Cartesian plane equation actually comes up in the formula book, but we've got n1x plus n2y plus n3z equals c, and that n1, n2, and n3 is still referring to the normal to the plane. So now we're going to have a think about the vector properties that you might come across. So one of them is going to be about the angles between different things. So between two lines that we've got here, we're going to say that cos theta is equal to the direction vector of one line dotted with the direction vector of the other line divided by the modulus of the direction vector of one multiplied by the modulus of the direction vector of the other one. And if you wanted to make the angle acute that we've got here, you just take modulus of the whole thing. So if it's negative, just make it become a positive. If it's between two planes, it's really the same as two lines, but instead of it being the direction vectors of the lines, it's going to be the normals of the plane. So it's going to be n1 dotted with n2 divided by the modulus of n1 multiplied by the modulus of n2. And if it wants you to give an acute angle, you just take the modulus of the numerator. You make the whole thing become positive. So the last one that we've got here is the angle between a line and a plane. The angle between a line and a plane is going to just be the plane's normal dotted with the line's direction divided by the modulus of the normal multiplied by the modulus of the direction. And this one, for sine, it does need to have the modulus lines around the whole thing to be able to give you the correct angle that you are looking for. Okay, we are nearly there now. We are going to be looking at these ones where it's more just a description here. I've got less to fill in. So we're going to be thinking about the intersections of different things, different lines and planes. So for two lines, you set R1 and equal to R2, you find lambda and mu, and it's really important that you check that they work with the k component as well, or the third component. Usually k could be another one. And they either intersect, they are parallel, or they are skew. So this first one here is them intersecting. This one is obviously them being parallel. And this one over here is skew. Skew is lines that don't intersect and they are not parallel to each other. You can check if they're parallel just looking at their directions. If they don't intersect, therefore they must be skew. So for the line and plane, I've got this diagram over here. You can see the red part is our plane and the line is intersecting at this place here. What you need to make sure though is that your plane must be in its scalar product form. That is the most useful form for a plane. All you then do is you substitute your line R into the R dot n equals D, which is your scalar product form of the plane, and then the rest of it will just work out. This one isn't technically in the spec, but there's an exam question that asks you to think about this, so I want you to have a think already. 2 planes here. It says find 2 points on both planes and then find the line through them. So if you look at this diagram, here are the 2 points that are on the plane, and then you're just going to find the equation of that line through them using your vector knowledge. Well, how do you find 2 points on both planes? What you do is you let z or x or y, you let it equal 0 or 1, something nice and easy, and then you just solve it to find out what x and y are, and then you'll solve those simultaneously, and then you'll have 2 coordinates. One of them will have z as 0, the other one will have z as 1, and then you can just find the equation of the line that goes through those 2 points. So we're just going to now talk through the rest. There's nothing really to add on to these diagrams. We're going to be thinking about the shortest distances section of vectors. So this is all to do with these things being perpendicular to each other. First of all, you're going to have a point and a line. For a point and a line, which I've got over here, you find a vector between a point and a general point on the line, meaning it's going to include lambda, and you make this perpendicular to the line direction using the property that when you dot them, they equal 0. That will give you lambda, blah, 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 and you can keep going through. Between 2 parallel lines, you do the same strategy of finding a vector which is between 2 general points on the lines. And then there's this little trick of, instead of using lambda minus mu everywhere, or mu minus lambda, you can replace that with a third parameter, usually t, and then you can make that vector perpendicular to the line direction, again using the dot product being equal to 0. Between 2 skew lines is really the same sort of strategy here. You find the vector between 2 general points on the lines, but this time you make this vector perpendicular to both of the directions, which will give you some simultaneous equations, and you can solve that to find out the solutions of what you're looking for. This one is in the formula book, and I don't ask my students to memorize this one. So to find the shortest distance between a point and a plane, the point is alpha, beta, gamma, and the plane in the formula book is in a slightly different form to how we see it. That distance is just equal to what we've got written here. So you've got the normals multiplied by the x, y, and z coordinates, and you add on d. Just careful here, d is on the left-hand side. I think earlier on we often think of it on the right-hand side. And you just divide it by the modulus of that normal vector. If you have 2 parallel planes, all you need to do is just find any point on one of the planes, and then you can use this formula that you've got here. It's really easy to find a point on a plane. Just find 3 numbers that satisfy the Cartesian equation. We've only got this last section now, which is some reflections that we have. So for vectors reflections, if you are asked to reflect a point in a plane, well, what you do, here's my point, and this is the plane. The first thing you do is you find the intersection of the normal through the point and the plane. So I'm talking about finding this point that we've got here. You obviously need to do some stuff to do with lines as well. Then you add this vector onto the intersection point. So you'll find out what this vector is, and then you add it onto the intersection point, and you end up at the reflected point on the other side of the plane. The last one, which is perhaps the most challenging one, is to reflect a line in a plane. So the line I'm wanting to reflect is this black line. This plane that I've got here is the red line. Well, the first thing that you do is you reflect any point on the line in the plane using the above. So you're going to take this point and you're going to reflect it over here. Then you find where the line intersects the plane. So here's the line and it intersects the plane here. So we now know this point and this point. And the last thing we do is we find the equation of the line through the intersection point and the reflected point. In other words, finding the equation of this blue line through the intersection point and through the reflected point. And so this is everything that you need to know for Core Pure 1 for your exam. There's a few things in there that maybe you think you know them off the top of your head. That's great, they don't need memorizing, but I think there's some useful bits, particularly for the new stuff on matrices and systems of equations and some of the strategies for vectors. If you can have those in your head, you're going to put yourself in a much stronger position during the exam. Well done for making it to the end of the video. I've put a link in the description to my Google Drive where you can get the filled in version of that PDF and also a blank version so that you can test yourself and see how much you've remembered. In the video description, there's also loads of links to the tutorials that I've actually got that will help you for any of the parts in the video that you may have found a bit confusing or a bit tricky. Lastly, if you found this useful, please do subscribe to my channel, like this video if you enjoyed it, and go and check out some of the other video tutorials that I have, because they might help you with some of the things you're finding difficult at school at the moment. Good luck with your revision, and I'll see you soon.